And welcome to the stream if you're watching this in the future or tuning in right now. So in our last episode, we actually created a system that is able to render 3D primitives which is a fine set point for a application. I just wanted to do some different stuff here that were promised earlier. We will do our uploading handler in terms of passing things along to the default heap on the GPU, and in that turn we will do so-called resource barriers. And I thought that we would do index buffers since they are fairly simple to implement. Lastly, we will do an intermediate episode let's see, where we add normals to our pipeline and by using some data from a simple Blender model, and then in the 6th video I thought we might do maybe a small material system, and I'll quote that because it's not really going to be a material system per se, but it will contain the so-called diffuse color, meaning the base color of the object, and then we will start working on and maybe implementing a simple toon shader. And this might be our 7th video, depending on a light source. Yeah, so that's the overall plan. I don't think there will be any more videos than that, because then we will have a system that is doing basic shading, doing basic lighting, and well, I think that it is a great endpoint for this tutorial. Yeah, so we will do our video series like that, and then I think I'll probably be done for today, unless I get spare time on my hands, and maybe get a new idea about something that I want to implement. Yeah, but I think that wraps this tutorial series up nicely and um, creates a um, um, set point in terms of where this application will end up, and it will show case how to do different stuff. Yeah. All right. Let's get going. I'll start the recording for the video series in just a moment. If there are any questions in terms of the previous series, feel free to ask them during the live stream. I will answer them when possible during um, the intersections between video recordings. Yeah. Okay. I'll glance at the the chat from time to time. Let me see. Um, but otherwise, I'll try to focus on this. So we would like to be able to transfer something from our upload heap, and we will start out by focusing on that. Let me start the recording here. Hi, and welcome to this next part of our tutorial series on how to do a DirectX 12 application from scratch in C++. During our last episode, we got to render parts of a 3D primitive, but there is one problem. We're spending a lot of time defining vertices that actually overlap. So we would like something called an index buffer. Yeah, so we will create that in our API. We will start out by creating a dynamic index buffer, but we will change that in the later part of the episode. We will also be creating a index buffer view, and we will be binding it to our draw calls and pipeline. So as many times before, a buffer is fairly simple to create with the API that we've created. We will create the index buffers down here. We will create it as per usual. Not the view, excuse me, the index buffer itself here. We will initialize that. We will create it on the heap. Right now we're allocating a lot of memory, or rather 16 kilobytes. That's not a lot of memory. We don't need to do that. We can of course do dynamic allocations, meaning that we can make sure that our application only allocates as large buffers as and a buffer that only is as large as needed. But yeah, we won't care about that. An index buffer is simply like a vertex buffer, except that it only contains indices in series of 3 if you're drawing triangles that map which vertices to use. So it's basically just lists of indexes. We will return to how to create them shortly, but we will create a view for the index buffer. we will specify the let's see, buffer location. We will specify the format. We will specify, let's see, do we have, hello. I'm happy that it all worked out in the end. So we probably need something like a 30-bit uint or something like that. 32-bit, of course. So let's tell the system that we will use that. And well, the size is our overall buffer size here. And that's basically it. That's the view for our index buffer. And now we can actually bind it to our pipeline, just as we bind the vertex buffer. Set index buffer, and we will reference the index buffer view, dynamic index buffer view. There we go. And everything should be bound. Right now we're not using it because we're not doing a draw command that is actually indexed. If we wanted to use our index buffer, we would simply call this method instead, draw indexed instance. And you would specify the index count per instance, meaning that we simply read the index buffer instead of the amount of vertices. And right now we will set that as 1, and we will create offsets into our buffer. So this is the parameter that we would supply. But let's set up an actual index buffer here so that we do not need to recreate all these vertices. We could say that the one that is negative is 0. This one is 1. And this one is 2. And if we simply start creating, let's see, a series of uint 32, because that's what we promised the system that our buffers would be. And let's just create 10. And if we simply start by setting our first index as 0, because we saw that we wanted to draw the vertex number 0, and then we set the second one to 1, and then we set the third one to number 2. Let's move our camera here back in line with, whoops, I just simply flipped the camera here. I, of course, meant to set the X as 0. So let's swap to index-based drawing. We will do a shortcut here again. We will define global max indices, or rather indices. Let's do 16 for now. And we will draw our primitives. Well, it's not undefined. It just hasn't woken up yet. Okay. Let's do 3. Right now, nothing is happening. It might pertain to... Oh, wait a minute. We do not upload the actual information, so that's why. Okay. Let's do this on the vertex buffer here. Let's do this on the vertex buffer, and then we handle the index buffer code all by itself. We of course need to do the mem copy since it's currently initialized, but hasn't been assigned any information. Let's do the index buffer here and get the CPU memory address, and then simply pass in our indices. Where it's an array, so it's a memory location anyway, and we do a g indices times a uint 32. Whoops, the size of course. So now we should copy over our indices here. Yeah, we get our first triangle. Let's move a bit down with the camera so that things look a bit more normal. So yeah, then the next position here, the first part of our next side here in the actually, I think maybe we want to do something that I thought of doing straight right now instead. Maybe we want to deprecate or rather disable this. Let's see. And maybe we want to disable this for now. And we will simply, I have a simple cube from Blender that is exported in OBS that we will use as a template for our actual model here, because that is already indexed for us. And okay, so we have our vertices here. We have to define 8 vertices, and as you can see, this is the power of indexed drawing. And even with 18 vertices, we weren't even able to draw a whole box. So we will do 8 vertices, and we will simply create our box from this. Let's see, let me copy it over so I don't have to swap the windows all the time. So we set the first vertex position as specified here. We take the positive x and the positive y, and then the negative. Wait a minute. This model might actually be in a right-hand sided coordinate system. So yeah, I think let's do a short thing in Blender here. Let's just simply create our box so it fits our needs. So we will just do a 1 by 1 by 1 box, and we export it as wavefront legacy here. And let's find our stuff here, the YouTube repo, and we in our application here create a folder, models, and then we want to create a box that has a positive C axis forward going. It also has a positive Y going up. We don't need to apply modifiers. We would like to write normals, but for a toon shader, we don't need UVs. We don't need to write materials, but we want groups of triangles that we can use to interpret how to render our model. So we will do a cube here, export that, and now we only need to know that Blender flips the winding order, because it's using OpenGL as its base. So that means that we need to flip every set of phase indices so that we draw in the opposite direction of that of Blender. All right, let's see. Our model looks like this. We have our normals here and we have our vertices. So let's just copy that in and start doing our vertices. Okay, now we're going. Let's see, we can simply copy this and space it out with a comma. Now that's fairly easy. One, let's do several of these. Two, better to use the mouse. And better to simply create several here. 5, 6, 7, 8. Ah, no, not 8. We already have 8. Okay, and then we take the second one. Then we take the third one. And of course we need to comma separate them. There we go. So that's the third one. Fourth one. Fourth one. Let's do a space here. Fifth one. Sixth one. The seventh. And lastly the eighth. Great stuff. So now we have our vertices. Let's see what happens if we draw. Let's see. Okay, we have an error somewhere. Something I. Oh, there we go. G indices. Well, did we comment out that word? No. Wait a minute. There we go. Okay, we still have a triangle. Let's move this out of the way. We don't want to look at that too much. So we will store our old inefficient box down here. This will simply be our vertices. Now we need to interpret how to build the actual box. So this is the face values of the box. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 faces, which is, or rather, yeah, triangles, which means that it has 6 faces, which is exactly right for a box. But we need to remember that these indices here need to be swapped in order. So number 0 here, let's see, we have 12, no, 12 times 3, that's 36 indices. So our first face will be consisting of let's see, they are actually not 0 indexed, so we need to subtract 1 every time. So let's start from the right and go towards the left. So the first one is 0. The second one is 2, and the last one is 4. Let's try that. We do get a face of some kind. Maybe we're starting with the top of the box. Our next face, let's just delete this one, will be number 3, number 7, and number 2. And let's do one more face here. Whoops, we of course need to update this as well. And we do 6, 7, 8. And we do 7. Whoops, 7, 5, 6. And let's try that. Let's just delete this one to make sure. All right, we're starting to see something that looks like a box. It's hard to discriminate since the colors are the same, but we can always change those if we want to. Maybe we want the second half of the box here to have a color of red so that we can clearly see the different sides of it. And we will, of course, update these as well. Okay. We do our next phase here. 9, 10, and 11. We need to do 5, 7, and 1 here. Delete that. And we do like this. And we do 1, 3, 0. Delete that. And we should have half our box here. We're starting to see how that looks. Let's do the next ones here. Oh, Karim, that sounds a bit ambitious. And that will take a long time, and yeah, I need to be working on my own project, so I will probably not do a tutorial series on those subjects unless there is many people who request it. I'm not doing this full time. I have a job that I need to take care of, as well as a girlfriend and other people. So it's a nice suggestion, but I simply do not have the time. Let's see. We're getting closer to being done here. Yeah, I will. But not as a tutorial. This is a tutorial series, so it's more elaborate on what we do when I need to do a lot of more work to make it work. So yeah, on the other streaming series, I will probably do something to the like of it, but not during this series. The source code is also different between the projects here, so this source code is way more simple. Let's see. And we're about to be done. Did I miscalculate somewhere? Let's see. 104. Is it really 38 vertices or indices? 39. Let me see. Did I skip something? 6. Let's try 39 then. All right. It seems our cube has been fully constructed. Let's move the camera off to the side. There we go. We have a 3D cube. that uses an index buffer. And as you can see, you provide a lot of different floats for just one vertex, but for one index, you only create a uint32. You could even compress this into a uint8 if you knew that you weren't going that high in terms of indices. It depends on the size of your models. Okay, so I plan to do normal importing as well. We have the normals here and can easily create a series of normals for each unique vertex position, which is actually 38 or 39, as you can see, potentially at least. No, not potentially. In fact, and we would need to expand this list a bit and do some more computation. So I'll skip that in this episode, and I'll do the implementation of the GPU-sided uploading system. So in order to upload something to the default heap, we need to create a buffer on the default heap. Then we need to change the state of that buffer into a write state, and then we need to create/use a buffer on the upload heap, as well as a command queue, a command list, and of course synchronization to upload the data. And then we need to transition the default heap buffer into a read state. So we could do something that simply does sort of that work for us on the resource itself. I think it's a fairly okay way to do it. You could do 8 other ways. Maybe you wanted the graphics list to be able to do it. Maybe you want a system that uses a pre-allocated dynamic buffer that just uses that one as a copy source. Then you could kind of like get around doing these things. Maybe we want to do a simple upload system that doesn't take too long time to implement. Yeah, okay. We will actually do that since it's a bit more fun. We will create a folder that handles memory is supposed to contain memory management files. And let me see. We will create a class that is a well, it's a buffer uploader. We will just call it that. And we need to move it into the correct directory here. We want to create a namespace, and we also want it to be exportable, YouTube API here. And then we also want to create the namespace here, and it will actually inherit from our resource system. We will allow us to create a empty buffer uploader. We will, of course, create a destructor, and we will create a release function. Then we will store an internal buffer, a D12 resource internal buffer, and we will of course do some kind of upload function. We will implement this later because let's see, because it will need to take some parameters. Then we need to call release, of course. Then we would also like a initialize function, and we would like a ID 3D12 device pointer, since our resource needs to have that device to be able to be created. Then we also want a const uint memory allocation, and let's do that for now. Whenever we initialize, we simply call internal buffer initialize, and we initialize on our device, and we allocate the specified amount of memory. And since this is an intermediary in terms of uploading to the GPU default heap, we will create it as is. Okay. So our renderer here will have this subsystem. We do subsystems up here. Let's see. Memory management, buffer uploader. We will create a buffer uploader. Buffer uploader. And we will initialize it. We will do it before any of this. We will do it and system setup. Maybe we don't need that comment. We will initialize it. We will give it a device, a size. Let's allocate 64 kilobytes to it, and let's see that everything works. Everything works. So now we simply need to create a upload method, and we need to make sure that the things get uploaded before we move on, since we want to synchronize with our synchronize our different resources here. All right. Our buffer uploader here will now get a buffer upload function here, which takes a pointer to a resource that is a pointer to our destination. We could do an offset in terms of the destination, but we don't really care. We want a memory location from which to copy, so we will source data, and we will do a uint, a const uint, um, which is simply our size here. And we would also like to be able to call a command queue and command list. So we will take a pointer to a D12 command list. We will take a pointer to a D12 command queue. Whoops, not that. D12 command queue. And that will be it, I think, for now. So let's do some uploading. It's fairly simple. We simply map our upload buffer here. Maybe we actually want to simplify this a bit. Maybe we want to create a internal memory, which will be a null pointer, and then on initialization, we actually if the we should map this anyway. So we simply call internal memory equals internal buffer. Internal buffer get CPU memory. Now that resource is actually mapped, and we store the buffer here. If we call release, if the internal memory is set, we need to reset it. All right, so now we don't need to map our internal buffer, since it's already mapped on the D12 resource. And we can simply start copying. We want to memcopy here from our source data into our internal pointer here, internal memory, and our source data. And then we want to copy the allocation size. We could do a search. Well, okay. Let's create an uint internal max size, which will be 0, and we will set that to our allocation size at allocation time, which means that we can do a YouTube assert. The size is lower than our max size. This will only run during debugging. So, and then we want to record our command here. P command list as a GFX command here. And we want to specify the command copy buffer region. We need to get the destination resource interface, which we get here. We do not have an offset into our destination resource. but we could easily implement it if we wanted to. Then we have our internal buffer, which we also need the resource interface for, and then we do not offset into our internal buffer, but we copy our size here. Then we want to call what we usually call when we're done recording command lists, because we want this to be executed immediately. And let's look down here. Well, we want to close the command list. We want to execute the commands, but right now this will throw an error because this is not enough. We also need to transition the state of the actual target destination to be able to write to it, and afterwards we want to transition out of that state. So we need a resource barrier as well, and that actually needs to be done before our call here. Let's get the resource. We want to create a transition with no flags. And we want to, let's expect that our resource has something. Let's see, create committed resource. Let's see, we saw some specifications here in terms of resource states. Usually it's common. Let's see, we want to transition it into a copy destination. And then we of course want to add that barrier to our command list. And then we want to transition afterwards. Let's reset the barrier here. And it was previously a copy destination. We want shader resource now. Let's see, pixel, non-pixel shader, render target. We could do index buffer and vertex buffer specials, but let's go back to common, I think. There we go. And we of course want to record that resource barrier. Okay. So now we have a series of command list recordings. We will ask our command list to close. We would like our command queue to execute the command list. Let's see, git And then we want to wait for our call to be executed. And then, oops, we want to reset our command lists. All right. Let's see if everything compiles. Everything compiles. We are not using this function for anything yet, but we will test it out. So let's migrate our vertex buffer here. Let's create a non-dynamic one and simply disable the old one. Let's create a new view, which is also not dynamic, and let's set up this. So we want to release that instead. We also want to bind that instead. We need to, of course, clean up the code so everything will work here. We have a series of errors. Okay, let's see. We will initialize this buffer here. Let's do 8 kilobytes. And let's do a default heap. And let's do a common resource state. And then we need to, well, that's not what we're doing. We simply set the name here. Let's remove this. We're not using that anymore. The vertices are fine. We do not need to memcopy anymore. We need to create the view though. Let's see, and we need to, of course, still set the address, and we need to set it to the same size as up here. And now we would like to test out our buffer uploader. Whoops. Upload. Well, buffer uploader. Up. Did we initialize this one? Yeah, we did. Let's upload something here. Let's grab our vertex buffer as a reference. Wait a minute. We need to get the address of that, and it doesn't like that. It's actually because it needs to be cast as a pointer to our resource here, and our source data is this. Our size is the size of a vertex times box vertices, and then we have our command list, which we will get the address of and cast as a v12 command list pointer. Let's simply do this on a new line, and let's do the same thing for our command Q, except that we of course need a command Q pointer and our command Q here instead. Let's try that. It might not work as expected, but well, we have no errors. We have no problems. Let's see. It's not even whining. All right. We might be doing something pretty nice then. Okay, let's look at NVIDIA Insight here. What do we, let's see. Whoops, that's not Insight. Right right now we probably haven't found anything correctly, but let's see. Our resources, our vertex buffer here, it's on the heap, I think, default heap. So at least we created the resource correctly. It has a size of about 8 kilobytes, and it contains some information. So let's see. Does this actually look like our information? Well, yeah, it seems like it. Let's just double check. Okay. We see values that are highly similar. Well, it simply looks like it worked. So right now, this data resides on our default heap. We successfully uploaded it, and we created a method to upload every kind of data directly to whatever destination through the command queue and command list. Yeah. The only problem that we have is that we do not bind things correctly for some reason. Excuse me. Let's see, does this actually record the geometry? Well, it does record the geometry. Did we change anything in particular? That's probably something that we forgot to change. Maybe it's not shader visible actually. Let's see. Did we get any warnings? Nope. And our vertex buffer view here is bound, and is it correctly set up? Strident bytes. Resource state. Let's see. Oh, okay. Okay, so we actually want a special case state. Let's see, the D3D12 resource state. Custom state, which will be D3D12 resource state common as per default. We will just copy this inside our buffer uploader here and then store it down here because we want to be able to access this as a vertex buffer. And we of course need to update the method here. Okay. And of course we do not want to redefine that. And then we do a if it's that, then otherwise we simply set it to our custom state. Therefore, in our render API here, we can actually specify that we want to end up in a constant buffer, vertex buffer state. Let's see, we have a problem somewhere. See declaration. Okay, it doesn't recognize. Oh, it doesn't recognize it. Now it does. Maybe. Oh, okay. We can't overwrite whatever. Okay. There we go. Everything is back to normal. So there was a custom resource state for vertex buffers and constant buffers. All right, let's do the same thing for our index buffer. And we can actually delete these because we don't want to use them anymore. And our vertex buffer gets created right there, and then it gets uploaded. Our index buffer gets created right here, and we want to create it on the default heap at a common resource state, excuse me. And we do not need this anymore, but we want to use our buffer uploader method, but we do not want a custom resource state. We want also the size of the amount of indices, and we want a UN32 instead here. And we want to store this information, and we want to use this buffer. Then we want to change these, and let's set this, and while I remember it, set name index buffer. We upload the data. We did this. We did this. Okay. We create our pipeline stuff. We do some math stuff here. And we actually ended up succeeding in reaching our goal. Great stuff. Everything should still work when we update the index buffer view here. Index buffer view. There we go. I think everything will still work. Everything works. All right, so now our resources are not created in the shared memory where you have to have the performance penalty of reading information that is also available to the CPU as a write destination. Now you get the maximum performance in terms of the actual vertex and index buffers. They get uploaded at their appropriate locations in GPU memory. All right, so let's look at the episode outline. Oops, it's not down there. The episode outline, didn't I do an episode outline? Did I delete it again? No, I did it here. So the fourth video here would be pertaining to uploading the data. We did a bit about resource barriers. I didn't really talk a lot about them, but especially when you're handling resources that reside solely on the GPU, you have to make sure that they are in the right state. The common state is not something that you can write to, so we change the resource state from common into a copy destination. And then after we did the copy, which is this command here that we register on the command queue, or rather command list, we change the resource back into either a common state or a particular custom state which is required for some resources, or in case we want to. And we collect these command list commands, and then we close the command list, we send it off to execution, and we wait for it to be done. You don't need to do this since since after the initialization you would do further command recordings, and eventually you would have a synchronization point. So it doesn't really matter that much, but since we're using the same buffer and we have no control over its internal memory, and we're overwriting every time we try to upload something, our internal buffer gets overwritten with whatever source data we have. We need to kind of flush the buffer and make sure that everything is uploaded before we write something new to it. So you could, of course, do a linear buffer or a ring buffer system in terms of handling this, but that's way more advanced and out of the scope for this series here. This will work perfectly fine, especially if you do initialization time uploads. If you do real-time uploads during rendering, it will probably have some performance penalty, and I would suggest that you, if you're trying to do something like that in the future, create a separate command queue that only have copy commands, and a separate command list, of course, to feed that command queue, and that you implemented a ring slash linear buffer, and that you yeah, study a bit about resource synchronizations and so forth. So yeah, it's a more advanced topic, and is part of the power where DirectX 12 allows you full control over your resources and how to manage them. So yeah, with great power comes great responsibility, as they say. Anyway, I think this episode has gone on long enough. We did excellent work, if I have to say it myself, during this episode, and we actually achieved the end goal of the original outline of this series. But as I've mentioned during the stream, I want to take it a bit further. I want to create a simple cel-shaded application that has a simple light source, light system and a material system. And you guys might know cel shading. It shouldn't be that hard to do. We simply need some normals in terms of our model, which we have from Blender here, right here for each vertex, and then we have the specification of which normals to use at which vertex for our box. So we will spend a video on kind of collecting that information and storing it and uploading it to the graphics pipeline. Then we will do a short video on a very, very simple diffuse based material system, and as a replacement for color, maybe, yeah, yeah, I think we will do that because it shows how to expand the generalized pipeline. And then in our last video, we will be writing some shader programs and some tools in terms of controlling a light source. We will start out by hard coding the light source, and we might do an 8th video where we simplify slash make the light source controllable from the application side, meaning not from the shaders. Yeah, so we will do that. I'll end off this episode, and hopefully you found this helpful, inspirational, entertaining, or maybe just something else entirely. Feel free to comment, like, or subscribe. And follow here on YouTube or Twitch. And thanks for dropping by. Hopefully I'll see you in the next one. As for the stream here, I'll just sort some stuff. Let me upload the video here. Let's see, we got to part, what is it called? Let's see, let me just fiddle around with this. So last episode was part 18. And let's see, let's do a commit here. Part 19, index buffer and upload system. Index buffer and upload system. I can actually fit it. Okay. Let's see. This should publish the episode. Whenever YouTube has checked through it. Okay. Great stuff. Any questions in terms of chat or anything I need to elaborate on? Before we move onwards. I'm not seeing anything. Maybe we just want to move on. Let me see. Did YouTube now mess up somewhere? I think, let me just check. I did specify. Yeah, I did that. Okay, well, so far no questions in chat. Let's move on to the next episode then. I'll start the recording in a short while. Yeah, I'm definitely feeling a bit excited about the Toon Shader stuff. Okay, I'll start the recording. Hello and welcome to the next episode in our DirectX beginner tutorial series, where you will see how to create your first DirectX 12 application in C++ from scratch. During our last episode, we did some generalized resource and memory management in terms of the GPU. Be sure to watch that episode if you want to learn a bit about that. Right now we're in a state where we can render a 3D cube, which is basically a hard-coded version of this cube object that we created in Blender. In this episode, I will extrapolate the what do you call it? Normals, and we will actually create a expanded version of the vertex set. So normals control how lighting is handled in terms of the object in 3D space. So we would like to create some sort of lighting information. Yeah, we need to change the layout of our vertex data structure here to support normals. Normals are basically just vectors that describe how the surface is facing and how to expect light to sort of bounce off the surface itself. Since we will be changing the way that our coloring system here works, we will actually be removing the color input here from our data structure. This means that because we've changed this, we also need to change our input assembler here. Let me just cut out this and store it for future reference. We will call this normal, and we will specify the exact same parameter as the position. Inside our renderer API, we will now not have support for the color part of the vertex struct. We will remove that. And inside our actual shaders here, we have to change this into something else. We don't mind passing on a color for the pixel shader. Right now we do not need to change this. We will simply supply the pixel shader with a white color. Right now we only change the input assembler part of the pipeline. As you can see, everything now gets rendered to a white color because we told our shader program that we want to do that. So we want to create pairs of vertices with some normals. We have 6 normals, one for each face of our box here. But we, when we use the normals, we need to create unique vertices because there might be more vertices than we have now, because the same vertex might have a different normal depending on where you look at the vertex from. If you're looking at it as a part of a face that is pointing in a certain direction, the normal will be different than if you're looking at the other face where the vertex also is used to draw the triangle. So we need to create vertex pairs here. And we need to do some processing of our indices as well. So we need to kind of rewrite a lot of these things. Okay. I think we will create them face by face. So this will be a vertex that has the first normal and the first vertex. This means that this vertex here will have the following normal, this one. And we will comma separate them. Okay. Then our next vertex will have, right now we're actually doing them left to right. Well, that means that we don't need to do the indices left to right, or rather right to left. Yeah, we can do that. Okay. So the next vertex here that our face specifies has the vertex information number 2. This is basically number 3 here, because yeah, let's just use the Blender enumerations here. So vertex, yeah, you have to imagine that this is a +1. Then the second vertex will have the this vertex position, but will have the third normal here. Okay. And then we will have our third vertex here. That will have our fifth vertex position here. And our first, wait a minute. Okay. We need to, my mistake. Let me see. The first one has the first vertex and then the first normal. The second one has the third vertex and the first normal. Well, all of these have the first normal here. And right now our index buffer goes 0, 1, 2. Okay. Well, that was that phase. Now we create the next one. Let's just copy this and set the vertices accordingly. Yeah, it's far easier to use an OBJ parser, which I've written, but yeah, you have to bear with me through this episode here. So our next vertex will have the fourth. Let's see, I specified this one as, yeah, the fourth vertex here. and it will have the second normal. This one will have the last vertex. And the second normal. And this one will also have the second normal, of course. And it will have the third vertex. And right now our index buffers go 3, 4, 5. Great stuff. Then we need to look for duplicate vertices. A duplicate vertex is something that has the same normal and the same vertex position. We probably won't experience that during the first part of the box here, but we might. So let's be mindful of that. Let's create the next 3 vertices here. 6, 7, 8, and they probably share the same normals here. Yeah, they all want the third normal. Therefore, we will give it to them. We will give the first one a vertex of the 8th vertex, then we will give the next one the 6th vertex here. And then the last one the 7th. All right. And our index buffer here will be 6, 7, 8. And let's create the next ones here. And they will all have the 4th normal. So far only unique vertices since we haven't used the 4th normal yet. We will use the 6th vertex position for the first one here. We will use the 8th vertex position for the next one here. And we will use the second vertex position for the last one. All right. We're starting to overflow here, but that's all right. Let's do 9, 10, and 11 here, and increase the size. Let's do 16 for now, and make Visual Studio not whine too much. Let's do 12, 13, 14. Okay. Now we're getting to the next one, the last half of each face, or second to last. They will all have the 5th normal. This means that the first part of the box do not have any overlapping vertices because they all have their own unique normals. Let's see if we take the second vertex here. Whoops. And we take the fourth vertex here. And we take the first vertex. Great stuff. And we add 12, 13, 14 to our index buffer here. And now we're doing the last part where we can expect only to see unique vertices. So we will do the vertex normal number 6 here. And then I'll space it out, or rather separate it. And for that we will use the 6th vertex for the first part of the face. Then we will use the second vertex for the yeah, and we will do the fifth vertex for that. Okay. We of course need to update the indices here, 16, 16, 17, 17. Okay, so we do 15, 16, and 17. But as you can see here, we end up in a situation now where this vertex combination with this normal combination, this vertex and normal combination has been used before. It was actually the third vertex that we ever did. This means that this face consists of 2 previously known vertices and 1 new. As we can see here, this is our second vertex. So let's do a new line of the index buffer. The first vertex of this face here is number 1. Then we will need to create a new vertex. New vertices, which we call number 18, and which uses the first normal, but the 7th vertex, and we simply specify that the next part of the face here is vertex number 18, and then we see 5.1 has actually been created before. It's number 2. Okay, that was that face. Now we'll take the next one. We see that it starts with an 8.2. That's our number 4. So therefore we start the face with a number 4. Then we have a 7.2. That's a new vertex. So therefore we create that. It will use, as we can see, also vertex number 7, but it will use the normal number 2 instead. So we will use vertex number 7, or rather 19, and then we see 3, 2 has actually been used before. It's number 5. All right. Let's do the next phase here. We see that the first vertex is 3, 3, 6, 3, meaning that it's number 7. And then 5, 3, has that one been used before? Let's look at our list of 3s here. Nope, that is new. So we create a new vertex for that one. Phi 3 is our fifth vertex here, and our third normal. This means that this face will have the vertex with the index of 20, and then we need to look up 7.3. Do we have that one? Yeah, we do. In our third face, it's the last component, meaning 8. As you can see, the pattern is almost certain already. We kind of, for each of these last faces, reuse 2 vertices and potentially create a new one. All right, let's see, 7.3, it was the 8 one, so this is the next one. We use vertex 8, 4, which is our number 10 here, if I recall correctly, yeah. Then we have a combination of 4, 4, which is probably new. It's just expected, but I'm pretty sure it is, yeah. At the list here, we see that it is new. Let's remember to copy the sign of the vertices here. And 4, 4, so it's combined with the fourth normal here. So we have our 21 here, and then our last vertex is our number 2, 4, which is our 12th vertex, meaning that it will have the number 11. All right, we're getting really close. We're almost done doing this work here. Okay, 4, 5 is actually created during one, let's see, 1, 2, 3, 4, 5, and 4, 5 is the middle one of our fifth face. So 1, 2, 3, 4, 5 is the 13th vertex, and we need to create a new vertex here. That is a combination of vertex 3 and the normal number 5. And we of course specify that, and then usually it's number 14 maybe. Let's see, 1, 5. It's the last of the fifth phase, so that's number 14, yeah. And then we do the last ones, 2, 6. It's the middle one of this, and then we combine the first vertex with the sixth normal. And we do number 23, and usually it's number 17 then, 1, 5, the last, yeah, let's do 17. Okay. That's it for our vertices here. We have 23 unique vertices. We have a series of indices here. Each vertex now has 24. Hello, welcome. And we of course need to update our list here. So we will create phase number 1 here. Phase number 2 here. 4, 5. 6, 7, 8. 9, 11, 12. And remember we flipped them since we created them in the opposite order. Let's see. Okay, so we go all the way up to 17. So let's do 12. Wait a minute. Yeah. 14, 15, 16, and 17. And now it gets a bit more tricky. Let's see. We don't need this. We can simply store it up here. And then our next list here is 1. Did we? Oh. No, it's right. I just thought we didn't offset. But surely we did. Then 4, 19. Oh, I already did. It's just not part of this tutorial series. I did on my primary project, which I do work on the live stream. But since I supply the source code for this project freely on GitHub, I decided not to use the library that I've written for doing that kind of parsing. So and I'll just be done in a minute anyway. But yeah, you can of course use a file parser, a obj loader, or something that you would like to use instead of doing this. If you're watching in the future, you can also just download the source code here when I'm done uploading the episode. Let's do 16, 23, and 17 here. And probably that is it. Let's see. 36. Let's try that. Well, we still have a box, so that's great. Now our data is updated with the normals for each vertex. So in terms of the video series, I will be ending the video series here since I simply wanted to do a short video about doing this normal handling stuff. Also, if you want to write a file parser yourself, yeah, sure, you're absolutely right. If you feel like Citizen Jags that a file parser is the way to go, you can definitely do that. I do that in my primary project. I do file parsers all the time. The problem with file parsers in terms of OBJ models is that you have to implement handling of when the vertices that you try to allocate are unique. I discussed it at length in a previous stream on my primary project. There's an episode where someone on Twitch asks about how to implement the OBJ file loader, and you can watch that stream if you're interested in seeing a way to do it at least. And what some of the edge cases and problems that might arise when you do that kind of file passing is. It will not be part of this tutorial series since we focus on the actual DirectX 12 and the graphics programming needed to create a simple DirectX 12 application. So but definitely it's a good suggestion, and it removes all this tedious work that you just saw me do for maybe 20 minutes, a half an hour. So it's highly recommended. It really saves you the time overall, and yeah, it makes you also able to load more complex models. All right. I think that is it for this episode. I'll stop the offline recording here and upload the file to YouTube. Hopefully you didn't find this episode too tedious. I'll try to preface the headline of the video that it's fairly light on coding. Anyway, hopefully I'll see you in the next part. All right, I'll just upload the video and then I'll continue onwards in terms of the next episode, which is a bit of a material system. Which we can use in terms of specifying a bit of diffuse color to our models, and then we will start doing a bit of shader programming in terms of uh, developing a light, a simple toon shader. Let me just upload the video. All right. We can close this one. We don't need it. And I'll sync the GitHub repo. Did we do episode 19 now, or let me see. No, 20. Let's see. Don't know why YouTube made a fuss about that one. All right, any questions before we move along? Mm, mm, mm. Well, it doesn't seem like it. All right, I'll just commit the changes. All right, if there are not any questions, we'll continue. I'll start the recording here. Let's see. All right. Hello and welcome to the next episode on this beginner tutorial on how to create your first DirectX application in C++ from scratch. Um, In the last episode, we created some normals and vertices for our box. We also changed the pipeline in terms of not using the color attribute of each vertex anymore, since we will be shifting towards a quote-unquote material system. We will create a simple material system that will apply a so-called diffuse color for our object. It basically means that what is the fundamental color that the object reflects when light shines upon it. Since it's diffuse coloring or diffuse lighting, it means that there are no reflections, there are no speculars on it, there's no roughness, anything like that. And that suits our outset or goal for this video series here to create a toon shader anyway, because we won't be doing materials in this shader. So how do we create a material buffer? Well, first we need to be able to bind our material buffer to our pipeline. So we need to update our root signature to be able to actually bind a data structure to another input slot. We would like to be able to change the color for future objects. So you could do that with a descriptor heap and a series of constant buffers. I do constant buffers page allocated in my own project, but for this project we will do something a bit more simple. We will simply expand our root signature here to contain another root parameter that is also a constant buffer with just the shader register 1 here. And we will update the number of parameters in the root signature in total. We will not be doing sampling since we're not doing textures, we're only doing materials. All right, so that's basically it. We've added a constant buffer to our root signature at the second input parameter slot. We would like for this constant buffer only to be visible to our pixel shader, since that is the part where we actually handle lighting and coloring of our pixels. So it's only relevant for that, at least for now. So therefore we set the shader visibility to that. We will create one material for this pipeline here. First, we need a render data structure, which we will call a material, cell shaded, cell shader maybe, and we will store a float 4 here, which we will call the diffuse albedo, and we will initialize that as black, but with an alpha of 1. Okay. We want to create a buffer on our render API here. Let's do a D12 resource where we set it as a material buffer 1 so that we could do several. And we, of course, want to initialize that. We will initialize it with our device. We will set it with the size of oh, wait a minute, we're creating a constant buffer here, so we need, of course, to create a aligned data structure that has some padding that fits the GPU cache of the different hardware vendors. So we do a size of a aligned size of the material cell shader. We want to create it on a default heap, and we want to create it in our resource state common, since we want to store this as something that we can access fast on the GPU on the default heap. And as you might recall from a previous episode, when we upload things that are vertex or constant buffers, we actually want them to end up in a specific resource state when we upload it. So let's see. We want to upload the material buffer here. We want to upload one material, and let's see, the rest is correct. Okay, let's just specify a name for this one so that we can find it inside our debugging tools material buffer. We will call it material constant buffer number 1. And we upload it to the GPU, but we haven't passed it any data yet. So let's create a material here. We will set the diffuse albedo to something like, maybe we want a primarily red color here, extremely red color, and maybe with a marginal of blue in it. Let's see, let's try that. And we simply reference our material here and upload that. All right. We've uploaded the material. Let's bind it to our draw calls here. We need to set the second root parameter to our material buffer GPU address, and now it's bound to the pipeline. This means that inside our pixel shader, we can actually access it. We can also bind it. Can you remember how we bind it? Maybe. We will simply call this material because we have no, we don't care. Maybe material data, and we will do a float 4 and call it diffuse albedo. And we will bind it to this pipeline. Remember, we can only do this inside our pixel shader because it's only visible there. And we will call this global material data, and it will be in our register B1. And now we can access it. So let's try doing that. Right now we will simply return the color of the albedo. Let's see, we have a problem in terms of the compilation here. Whoops. Undeclared name here. There we go. There we go. we suddenly have a material, but the material does nothing in terms of lighting, but at least now we can specify the color of our object here. Let's see. I wanted to change the color a bit, maybe tone it a bit down in terms of the blue. That looks a bit better. All right. So now we have a material that resides on the GPU default heap. And that's great. Actually, that is basically what I wanted to do. You could put these into a vector and create a series of different materials and simply just reference the appropriate material down here. You could do that. Well, maybe we want to do that. Okay. No. Well, maybe we will do that in the future. But since it's probably something that we would like to do, I think that we should actually move this step up here, create a light source, and actually collapse this into this episode as well. And then we can spend our next episode only doing the actual toon shader stuff. Yeah, let me see how far this recording went. It's only 10 minutes, so it's fairly short. So we will be creating some information that we want to what do you call it? Store in our scene here. We want to create a light structure. We want to give it a XM float 3 position, which we will initialize as 0. We want to, since DirectX 12 and shaders in general prefer things that are byte aligned with 16-byte alignment, I think, or is it even 128 bits, which would be 32-byte alignment. Yeah, I think it's that, but anyway, to make full use of the resources, we will have to try to arrange our data so that 4 floating point numbers are listed together, and then bigger structures are kind of like arranged so that everything is aligned nicely. So we will do something like a strength value that we will set to 0, and then we will of course specify a direction vector. And then we will do some padding here, which we don't care about. Because we will simply create a scene light here as part of our pass data. We will declare that inside our pass data struct here. We will create a light struct, which we will fill with a float 3 position, a float strength, and a float free direction, and a float padding. So now if we create an array of these, if we want multiple lights, um, we can always do that. Okay, light data, lights, maybe just one light. Okay, and since we probably want this in our, well, the problem is now that in our root signature we have actually specified this that this is whoops, that this is only vertex visible, but maybe we can combine flags. Is there a combined flag? Shader. Okay, let's do all. Our pass data will be available everywhere. All right, look, I think everything should compile still. Yeah, but right now we do not store any lighting information. It's fairly easy to store some lighting information. Whenever we, I think we do it in our update step here. And we could do a light array. Let's see, view projection, constant pass data. Maybe we want a lights, which support up to 8 lights. In our renderer API here, we set the first light position. Yes, maybe it doesn't. Maybe we don't want a light position. Maybe we don't care about the light position. Maybe we want a overall directional light, which will point downwards, straight downwards. So we do -1. We do a normalized vector here, and we can set the strength to something, maybe an arbitrary value of 1. We don't know what it does yet. And then we simply want to cast this as a byte pointer because we want to offset it plus a size t. Is that a size t? It is a size t. Okay, plus the size of the pass data, and we simply copy the lights here, the first one, and copy the light data structure over each frame. This should be, no, it's not fine. Oh, is that it? There we go. All right. Okay, we could do these initializations if we wanted to. We don't care right now. So now we can upload a light. We can set its direction and strength. We can control it all from the application side. And right now we are set up in terms of doing our actual shader program. Great stuff. Great stuff. So Yeah, maybe we want to do a last episode here, handling rotation of objects, scaling, moving. Yeah. Okay, I'll add that as a last feature. Now I won't be adding any more features, I think, because this project is kind of like growing steadily. Yeah, so that's it for this small video. In the next, I'll toy around with a simple toon shader. Yeah, so stay tuned for the next episode. If you found any of this helpful, useful, or inspirational, or if you have questions or something that you would like to know, feel free to comment down below. Also, feel free to like, subscribe, or in other ways support the channel if you enjoy any of this content. In the next video, I'll be starting on the toon shader. All right. Hopefully, I'll see you around. Bye bye. And here on the stream, I will just upload the video to the YouTube archive. Uh, let's see. And of course, I need to do the GitHub repo as well. So we've done episode 20 before. Excuse me. This is 21. Uploading material and lights. There we go. Let's upload that. YouTube is really slow at processing these HD videos, but the shorter videos, the faster it goes. Let me just check that the playlists are arranged as I want them, and then I'll start going. All right, everything looks fine in terms of the YouTube video series. All right. Any questions from any viewers? Anything you would like to add or discuss or criticize or something else before we move on? Uh, Let me just add this uploading material and lights data. Well, it doesn't seem like anyone has anything they want to ask or add or discuss. So I'll just move on to the next part where we start doing the shader programming. So I'll start the recording in just a moment. I just need to check that our GitHub here is updated. It seems like it. Okay, I'll start the recording now. Hello and welcome to the next part of the tutorial series on how to create your first DirectX 12 application in C++ from scratch. During the last episode, we did some uploading of different information. We created a material buffer that is basically a so-called diffuse albedo that gets uploaded to the GPU. And we specified it as follows: a material that reflects a primarily red light with a blue tint. And we also created a so-called lights, a directional lights, which basically just has a normalized direction vector and a strength to it. We also allowed the possibility of creating a position for the lights. Yeah, you can do as you see fit. We update the lights as part of a the pass data constant buffer that gets updated every frame, and we bind it to the pipeline. Actually, we haven't bound it to our pixel shader, but we will do that just now. We will do our pass data here, since it's the first root buffer, or rather constant buffer bound to the first root parameter. It will of course be in register 0. All right, now that is actually bound to our pipeline. We need to do some stuff in terms of our shader programs here. We want our vertex shader here. It takes in a normal, it takes in a position, it outputs a screen space position, but it doesn't output the normal. And we would like for it to pass along the normal here, which is the per vertex normal that will be interpolated between each pixel. Remember, the pixel shader and the rasterizer interpolates between pixels for you. So this handles everything per vertex, but it outputs something that the rasterization unit can use to actually draw pixels, and the pixel shader can use for interpolation. We use our pass data here. We output our vertex shader output here. We want to change our pixel shader input to something like that. And right now everything should work fine. We have no problem. All right. So right now we pass along our vertex information. We also have a light data structure. I would like to see if we actually have any information on the GPU in terms of the light data. So I'll, whoops. Okay. I probably have to move some shaders here. I haven't updated the shaders for the NVIDIA Insight part of the thing, so I'll just show you in our application here. We need the shaders, and we need to post them in here where NVIDIA uses the application. Yeah, it runs fine outside NVIDIA Insight, so let's try again. Now it runs fine. Okay, let's see if we can find our pass data buffer. We actually haven't named it. That annoys me a bit. This is an upload heap buffer, so it could be 255, 56 bytes. That could be our buffer here. Let's see. It would contain a view projection matrix, and then it would contain our float 3, float 3, float light data, right? Let's see. Let's see. Wait a minute. There's an error in our code. There's an error in our code. We do not want to offset by the whole. We don't want to offset the whole size of the pass data. We only want to offset the part with the view projection matrix, because we want the lights, of course, to be um, uh, first we only want to write the view projection matrix, and then we only want to offset by the view projection matrix. So now everything should be properly aligned in our video memory here. Let's see. What have you got for us? Oh, that's the description. All right, everything already looks better. As you can see, we have some information there. Let's see, float, float free, float. Okay, so our first position is 0, that's fine. Our strength is 1, I think. Let's see. Does that correspond to what we actually specified in here? The position is the first field, then the strength. So this should actually be ordered like this. And we could simply show the position here, although it's 0 and not needed. We can just do this so we can see the outline of the actual struct in memory. Okay, so that actually is correct now. Great stuff. So that was a small bug. Be mindful of your mem copies. It's easy to miss the target by a small to a large amount of bytes. Anyway, so our data is actually uploaded. That's pretty great. We will do some, try to do some shading here. Excuse me. We will try to specify an intensity of our light here. And we want to create a color that will be, no. And we want to specify the intensity by taking the dot product of our pass data, not material data, pass data, light dot direction here. I can't see anything there. And we want to take our input normal here. I can't see anything. And by doing the dot product, we find how much these two vectors align. If they are completely aligned, we will have a high intensity. If not, we will have a lower intensity. So let's just do something like this for testing. Then we will set the color to something, let's see, a float for with the color of red, a bit of green here, and a bit of blue, and of course an alpha of 1. Else if the intensity is larger than 0.5, we maybe tune down the color here. And we can do 25 here and do 6, 1, and else we will set the color as this. This is not really nice shader code, but hopefully it won't be too slow. And let's try that. Let's see. Okay, we can't open them. Whoops. Hmm. And then we perhaps want to multiply that by our diffuse albedo. Well, that didn't really do anything, did it? Let's see. Let's try to normalize this. And let's see. Okay, maybe we need to. Oh yeah, okay. I know why. I know why. In our vertex shader, we're not really transforming our normals here. We need to transform them. So let's do that. I think at least we need to do that. And then we will take the RGB. Wait a minute. Okay, there we go. RGB. Well, that doesn't change anything. Let me see in debug mode. All right, do we actually upload our normal data? Let's try looking at that. Okay, this has a different shading, of course, but let's see our vertex buffer here. Flow 3, flow 3. And let's do indices. Huh. Maybe I need to translate the normal in a different way. Let me see. What do I usually do in terms of that? Shader programming is not my strong suit, but I think we will figure it out. Normal world. Usually I would do like this. No, maybe I would. Maybe I would actually not do that. No, I wouldn't do this. That doesn't make any sense. Because the normal is in world space coordinates. Does this actually only work or what? Nope. Let's do the color for now. Maybe we need to. Let's try rotating the camera. Yep. That doesn't change anything. Oh, okay. I'm playing around with a so-called tool shader and the lighting. Oh, there we go. So the vector was not pointing in the right direction. So my stuff was actually correct. We now have a tool shaded square. It's not much, but it is something. And now we get the 3D perspective of things. Let's see. Maybe the material is a bit dim. No, maybe we want to tune it down instead. All right. All right, great stuff. Maybe this needs to be a bit dimmer because maybe the difference isn't that big when the lighting doesn't apply properly. Maybe you actually want to reset these and let the material drive the actual color of these. So let's just do these as scaling factors, and instead let the material decide how light or dark the thing is. So now we can control the material itself. A bit more here. Let's do 25 here. Okay. That's actually pretty decent. Okay. So now we have written a shader program that I have explained exactly nothing about. So let me quickly do that. We had our information bound to our pipeline readily available. There we go. So what we generally do is that we pass along our normal coordinates for each vertex into our pixel shader, which means that the normal position for each pixel is interpolated between the vertices that we're rendering, or if we're rendering some piece between two different vertices. We have uploaded some lighting data, just a directional light, which we also bind to our pixel shader here. Inside our pixel shader, we check if the direction of the directional light and the normal of the pixel are pointing in the same direction. If they are pointing in the same direction, it means that yeah, actually we could negate one of these, because right now, can we do that? Maybe we can do minus. Yeah, we can actually do minus because I want to change this so that it actually points downwards. Anyway, so if the opposite direction of our um, um, global directional light has the same direction as our pixel normal, that means that the light is probably shining directly on that pixel, and it will have a high intensity in terms of coloring. If it's in the opposite direction, we're probably not shining any light on that particular pixel, and therefore it gets darker. We simply specify a parameter here that is a factor that controls how intense the color is, and we multiply that by the material diffuse albedo, which is the base color that the object material actually reflects whenever it's lit. And that gives us this kind of perspective here. Let's try moving the camera a bit. Let's see, maybe we want to move even further out here and maybe a bit higher up. As you can see, everything has a nice 3D perspective in terms of some sides of this cube are more lit than others. So that's basically a toon/cell shader. You simply do simple lighting models, and yeah, if we had a more complex figure, you would be able to see more interesting lights. Yeah, you could implement a model loader and actually see how the lights would turn out. Maybe I'll do an example where we use our model loader and actually load some interesting models here. But for now, we won't do that. We will instead do one last important topic, and that is transforms, and we will use transforms to manipulate our object. Since transforms handles on a vertex basis rotation, scaling, and translation slash also called movement. So we will do that in the last episode, and maybe we will animate something a bit. Yeah, so that's basically it. Yeah. Maybe we will also do multiple objects of the same mesh, but with different attributes, since this actually allows us to do something like this. Okay, and I swear it will probably be the last episode. All right, any questions before we round this episode off? If you really wanted to see shadows, should we do it? Let me just check you, my friend. Can I react? Oh, it's hidden behind this or what? Oh, I hate the YouTube interface here. Let's see. Let's see. Well, can I do? Huh, that's weird. I can't choose reply. Okay, but anyway, I'll consider doing shadows. That's it for this episode. If you found it helpful, inspirational, entertaining, or something else, feel free to comment, like, or subscribe, or support the channel. Hopefully, I'll be seeing you in the next episode. Let me just copy over the shaders here real quick. For our NVIDIA Insight here. Oh, whoops. There we go. And let me do a upload here. So we were 21 before. Let's do a episode. Episode here, part 22, a simple toon shader. It's 22, right? Yeah, it's 22. Let's see. Can I really not tag you? Yeah, I can. Let's see. Any questions so far from anyone watching along? Uh, because we could probably, maybe if we have more time, I could do this shadow implementation, or at least look into some simple method. Since we now have directional lighting at least. Uh, yeah. We'll of course do the object transforms next here. Mm. Mm -mm -mm. Well, it doesn't seem that there are any questions or anything, so maybe I should just truck on, as they say, in terms of actually updating, or rather getting the next video done, and then maybe I'll do a break and I'll consider how to do, or rather whether to do shadows, at least some basic shadow rendering. Yeah. So far, there aren't any questions, or if you have any questions, feel free to ask them. Otherwise, I will be continuing onwards with the video series and start the recording of the next episodes. All right, I'll just get going. Hi and welcome to the next video in our beginner tutorial series on how to create your first DirectX 12 application in C++ from scratch. During the last episode, we created a simple toon shader that takes a material color and uses a global directional lights and calculates how the color should be on the object depending on its position in relation to the lights. It's a really simple shader program, but it works. Um, uh, in this episode, we will be creating so-called transform matrices. so-called transform matrices. Sorry, my headset is really bad. It just falls out occasionally. That describe how different objects are rotated, scaled, and translated. And usually an object has a unique transform in terms of describing its placement in the world. It also means that you can use the same meshes multiple times by simply just creating separate matrices that contain the rotation, scaling, and position of the actual object in 3D space. So we would like to be able to upload this information to our GPU. We want to do it on a draw call basis. Maybe not upload it per se, but at least be able to access it on a draw call basis. Therefore, we want to create a struct that we can upload to a upload heap, which will contain our object data. This will be a so-called per object kind of buffer, and it will contain a XM matrix actually called its transform matrix. And we will set this to be initialized as an identity matrix, meaning that the vertices themselves are not rotated, are not scaled, and are not translated in terms of their position in object space. This matrix here simply controls every attribute of the object. It can also create skewed objects if you want to. So it's a really nice data structure to be able to bind to your pipeline. As for our pipeline here, we want to bind it to the root signature, since we will be using our root signature arguments as a way to couple the transform matrix to each draw call. Since you should order your root parameters here in the order that they are updated, starting with the most regularly updated data structure. You should try to arrange them in such a way that that is upheld. So this is the past data. It's updated each frame, since the camera and everything else might change. So therefore, we need to update it each frame. Then we would like to be able to update the transform matrices. Secondly, because sometimes our objects move and therefore sometimes their transforms change. And then lastly, we want the materials bound because they are probably not changing. So therefore, they will be more rarely updated, and therefore they should be placed as the last argument of the actual root signature. So we will rearrange our root signature here, and our transform will be available to the pixel shader here, or rather vertex shader, because it will translate the vertices themselves. I'm pretty sure that we don't want to use the transform matrix inside the pixel shader. Usually I don't do that. But there might be a case where you want to upload it to your other shaders. Let's see. But now we change the order of the material and the past data, structure. our render API here will, the view projection matrix is something that, okay, we have vertex buffers, index buffers, materials, path data buffers, and lights. These are kind of like scene resources. So let's rearrange them. And let's create a vector of the 12 resources that we call our transforms. Let's call them object transforms. And we want to create object transforms. You kind of know the drill here. We will and place back a empty D12 resource here. And then let's see, we could be lazy and well, this doesn't actually return a reference. Okay. And then we want to access our transforms here by taking the latest object inside of it. And then we want to initialize that using our device. We want to create it with the size of our let's see, object data here. Let's see, that's the right structure. Yeah. And we want to create it on the upload heap. And we want to create it in the generic read state, which is usually what we do for our dynamically stored buffers. So we initialize it, and then let's see. We initialize it, and then we want to access it, or rather, no, we don't want to access it. We just want to memcopy some values over to it. So we will get the CPU address. Right now, we will create a null pointer, and we will write our object data. Let's just do a temp data here. Right now it will be an identity matrix. We're just gonna oh, wait a minute, I forgot that inside our root signature we of course need to create update our registers as well. There we go. We have updated our registers. Let's the pass data is still the same. The material data is now B2. Okay. Okay, we copy the data, and now we want to bind it to our pipeline. We simply grab this. We know that it's the first one that we're using right now. We will, of course, set the parameter here to 1, and let's do like this. So this should be fine. Okay. We of course need to include the vector here. Engine minimum. Well, okay. We could also do just the PCH. Does it contain vector? No, it doesn't. That's interesting. Usually I include vector as some of the first structs, or rather standard library functions. Yeah, okay, everything compiles. So now we need to bind our vertex shader to our data structure here. We will have a struct called object data, which will contain a float 4 times 4 called transform. And we of course want to bind that to our pipeline here. Let's see, we do object data here, and we bind the register here. There we go. And we need to apply our transform here to every vertex. So we will create a temporary position, which we will call world position, which will be our let's see, we will do our world position, which will initially take our original position, and then we will update it by multiplying our object data transform with our world position. And then let's see, we of course need to add an extra 1 here to the end because it's only 3 floats. And we will instead use that. Let's just comment this out and change this so that we instead use the now translated world position instead of our original position here. And we will, of course, grab the RGB here, or XYZ. Maybe that's more obvious what we're actually doing. The normal position actually also needs to be translated by the object data transform, because if the object is rotated, so are the normals. So therefore we need to update the normals here the same way. And we, since we pass along a float 3, we do XYZ here as well. Okay. Right now this shouldn't change anything because we haven't done anything to our transform, but under the hood everything now changed. Not everything, but some of it changed because now we can set our temp data transform here. The first register, maybe we want to set that to something like, well, maybe we want extra scaling on the x-axis. Let's try that. I've been doing a lot of different stuff in terms of register handling. Oh, wow. Would you look at that? We did X scaling. So that's great. I'm sorry about that. And as you can see, we simply now have a scaled object. We can change the Y scaling as well. go. We can also change the X position. I think it's stored here, but I'm not sure. Nope, it's not. The X position is then stored inside this. Okay, this is the Y position. Now it will move upwards. Yeah, as you can see. Let's try doing like this, and then maybe a bit out to the side here. Okay, that doesn't look pretty. Let's not do that. And of course we can change different attributes. Did it get more visibly lit? Let's just zoom out a bit here. Maybe do 8 and 8 here. Okay. Anyway, you can do all sorts of different transformations. Whoops. And yeah. Now we can do several instances of these. Let me show you. So let's just change our system here in terms of the material buffers. We will also do a vector of those. We will need to handle that. In place back a D12 resource. And we will simply do this totally manual like this, and initialize as before. I change this. And then we will of course also upload it. Let's create a scoped section here where we simply do material allocations. Let's do another material here where we set it to material number 2, and let's do a blue material. There we go. And of course we need to set that material to that address. Okay. And down here we need to set the appropriate material buffer here. And everything should still work, but now we have, oh wait a minute. We have an error somewhere. There we go. Redefinition. Oh. There we go. Now we can do multiple objects, but we first need to do this as well, preferably in the scope. Transform allocations here, And let's instead just do manual indexing here because it's a bit more nice. We will create a object with excuse me an identity matrix. Let's set the temp data transform last register to something like, well, we want a world space position -2, no, -3 on the X, well, still at the 0 on the Y, and then maybe -2 on the Z axis. And the last component can just be 0 here. Okay, so now we have created two transforms. We have created two materials. Let's do two draw calls. Right now we do a single draw call here. Draw call. Let's group it together. And let's do another draw call here, where we simply swap these and draw with a different transform and a different material. As you can see, the objects now have different positioning and different materials. All right. So now we have created support for transforms, materials, draw calls. Even though they're not instanced, you could optimize that and batch these together, but you would have to find another way of controlling their materials and their transforms. But yeah, basically you now have a application that can draw a lot of different stuff. We could do some scaling here on this object here. Let's try that. Maybe we wanted to scale it really small on the x-axis and maybe give it a bit of a skew on the other axis. So let's try that. As you can see, the object now looks different. This wasn't intentional, but yeah. And if you want to rotate it, you can also do that. We could, let's see, okay, when we close the application, we end up in a situation where we're not behaving as nicely. Okay, the shader. Okay, let's do some cleanup here. As we've been neglecting that. I don't think we should be able to reach a state where the bytecode was 0. I mean, okay, but let's go through our resource deallocation here. These buffers should auto deallocate. Let's see if they are mapped. We unmap. We reset. Okay. I'll consider it. Okay, this might relate to the vector handling here. Okay, we will do the cleanup step, and then we are actually mostly done with our series so far. I list in the material buffer size. Let's do that. Then we do the object transforms and release those. Let's see. Okay, now we're good. Great stuff. No problems. Okay, let's see, where else do we need to release? We need to release the index buffer. Yeah, we've been neglecting doing that. It probably wouldn't matter, but we like to have some proper control over our application. Let's see. Let's release the index buffer as well. How far have we gotten in terms of removing stuff? Oh yeah, the pipeline state, base pipeline state. It should release everything. And then we have a series of resources. Oh yeah, we of course need to release our buffer uploader. Release. Great stuff. And then we want our descriptor heap. That's the DSV. Release that. Let's see, do we have any more resources? Okay. It doesn't like when I okay, maybe I just yeah, maybe it's not even allocated. Let's first of all flush the command queue so that nothing is referenced. And then we have a couple of resources that we haven't released. We have the pass data. Do we release that? No, we don't. Oh, we do that twice actually. Let's see. All right, we have only one resource left. Okay, this might be pertaining to the vector. Yeah, that's a known bug. We need to implement a move and copy method on the resource. It will only be problematic when the application shuts down or if the buffers resize. Let's see, do we have anything else that we need to release? Maybe the depth buffer itself. And I think we're done. And let's see. Okay, we get that error, and we do get it no matter what I expect. No? Only when closing? Yeah. Well, it didn't complain this time. Let's see in our resource here if we can figure out the bug. On the destructor. Oh, wait a minute. Of course, we want to unmap here, and then we want to set that to a null pointer. That's a bug. All right. Well, all right. So this actually calls. Let's try stepping through. All right. All right. It accidentally stepped into something. Okay. So we now found the error. So it's during the okay. Let's see. We want to know which object it is. So let's get the application up and running. Blah blah blah. We don't care. Blah blah blah. Continue. Okay. Now let's close it. Okay. So this should be 0, meaning that we shouldn't unmap. Hello. I will implement that in my other series in my own game engine. That's a fairly complex um, problem that you uh, need to solve. You need bounding volumes, and you need ray casting and intersection testing for that. So, but if you watch my other streaming series, I actually, when I refactored the renderer, I end up doing that. All right. So watch this. Let's see. Uh, okay. So right now we do not have the problem. We are not releasing anything. Okay, now we're stepping into the object transforms, and we actually get an error here. Is it because I've never actually set the get CPU memory? Okay, so whenever we release that specific object, we get into trouble. Is it the same thing every time? Let's see. Yeah, it is. Let's also name the resources so that we don't have to guess. So we name this resource, oops, set name, transform 1, CB. Yeah. And then transform 2, CB. And we will know which object causes the error. Transform 1, CB. This sub-resource 0 is not mapped. Huh. It's not a critical bug since it happens on resource deallocation, but yeah, I don't think it's supposed to do that because the only thing I can think of is a custom copy constructor being called on the object, and the pointer being in a different state. Because I think if you watch closely here, if I take the vector and if I reserve 2 slots, which means it will not resize ever, it will just keep the same allocation size. No copy or move constructor will be called on any of these objects, and therefore their states will be exactly as we see them here. If we close this, yeah, now we don't get an error. So it's because of the custom copy slash move constructor, uh, or rather the default move constructor. So we need to implement that in our resource here. Implement move slash copy constructor for objects, since we store it in vectors and they resize. It probably just copies over this value, but it's never actually mapped. So we want control over how this information is transferred whenever the vectors resize. Right now this won't bug, but it's certainly something that needs a more viable long-term fix. But yeah, I think that's it for this episode. I'll be doing a break, I think. Are there any questions to the current episode in terms of transforms? Um, let's try toying around with the lights while people decide if they have questions. Thank you. Let's set up the lights here. Maybe we want a different light direction. Maybe we just want a light that shines down on these boxes. Uh, well, that definitely didn't work. And do anything interesting. Now that looks a bit more interesting, right? Let's zoom in with the camera here. Yeah. Maybe we will do shadows. Let's do a scene floor here, just to be complete, to show the uh, real power of our system here. So we create our material buffers. We reserve a size of 3. And yeah, you could do that, but I mean, it's basically manipulating this view projection matrix. So it's just it's not an difficult topic. You just change the position of the camera here. You manipulate this vector here. So um, since this is not series on actually how to implement controls and everything like that, but it's directly focused on the renderer part. I think even though we could do it, people can figure most of that stuff out themselves, I think. Oh, okay. Uh, well, just be mindful if you're using DirectX math, and that look at is um, a one version of the way to generate a view matrix. The other version is XM matrix. Uh, uh, perspective lift. No. What is it called? Look. Look to. Look at. Yeah, look to, I think. Look to, and you specify the camera position, the eye direction, and the up direction. This one is fairly easy to manipulate, since when you use this one instead and you change the position vector, everything just updates perfectly. The reason why this one is hard to control is because you're constantly looking at a specific point, and the math that revolves around that one is different. So if you want something like a strafe camera that you can update by using WASD or something, you shouldn't be using this one. You should instead use this one and define a forward-going vector. So you would do something like the vec3 position, the vec3 normalized forward direction, and then the vec3 normalized up direction instead. And you would simply just update this every frame. You could also rotate that in 3D space, and the camera would adjust. You could also update the forward going because the forward going vector, if you change this one and or the up direction while keeping the same position, it's basically yaw and pitch. So if you rotate this, you basically end up, if the camera is not pitched, you rotate around the y-axis, and this rotates around either, no, this actually rotates around the x-axis. Yeah. If you look into the math behind it, it probably gets more clear what you need to do. It's a fine suggestion, but yeah. I have a episode on doing a camera controller on the other streaming series, so I would refer to that, since no problem. But I'll definitely consider doing the shadows now that you've mentioned it. That's a bit more interesting topic, and it also is within the scope of actually doing a simple application that has lights, materials, and yeah, shadows. So we could definitely do that. Let's just add one material here. Let's call it floor, and set that to a gray color, dark gray color here. Upload that, and then let's upload this let's see, any other suggestions, comments, or anything while I wrap this up? XM identity matrix. Let's see, transform. Let's reset that one, and transform 3 floor. Okay, let's see, we will do a draw call here. Draw a floor, and we will bind this, and we will of course create a floor-like data structure here. So our position is supposed to be offset downwards on the y-axis, but otherwise just dead center. So we maybe do 4 down on the y, and the rest is going to be like this. And the scaling on the XYZ will be fairly big. So let's do scaling here. Let's do 100 in terms of scaling. and the last one. All right. Okay, it didn't work out totally as I expect. It didn't work out as I expected. Let's see. Did we create that? Maybe let's see if I just created. Okay, and let's check the color here. Haven't I? Huh. Okay, let's see what happens when we run it through direct our NVIDIA Inside here. I'm probably getting a bit tired and missing some stuff. Oops. Probably need to update some shaders or something. Let's try doing that at least. Oops. That's better. Did I not capture a frame? I did now. Okay. Yeah, yeah. It's usually related to the math when you don't see things correctly. Maybe, oh, maybe I need to change this. Load 3, right? Load 4. Well, that's supposed to be fine. Let's do our draw calls here. The last one, the geometry here. Well, it's the same geometry, of course, but okay. For some reason, it doesn't like something that we do. It's probably related to, yeah, I don't know. Let's do 10. Oh, okay. Maybe we're just, I'm so stupid. Now I know why it wasn't showing me us anything. It's because um, we were actually scaling it so large that it was we were inside it, and of course we only need to scale it on the X and Z plane. We actually want to scale it down in terms of the Y, and then we want to move it downwards on the Y. There we go. Now we have a plane of sorts here. Let's see. Yeah, you can use that. It depends on the type of camera you have. But let's move this camera a bit away. Okay. Yeah. this sets us up for doing maybe shadows if we want to. Anyway, I think this is it for this episode. I will be rounding off the video. Uh, yeah, I think everything is working as it should. And yeah, hopefully you found this helpful, inspirational, or just entertaining. Um, yeah, it's been a fun little project to do on the side of things. But yeah, I definitely also want to be working on my primary project. I'll consider doing the shadows as a separate episode here uh, in this series, and then I'll probably consider everything somewhat done. But we'll see. Maybe if there are a large number of requests in terms of simple topics, I'll add them. But please bear in mind that most topics in terms of doing everything from scratch is somewhat complicated, and even though it seems like a simple feature, it might require several additional components. Also, I might already have done it in my other streaming series, so feel free to browse through those episodes and see if there's something that you can use in that regard. I try to title things as appropriate as possible. Anyway, I hope you feel like liking, commenting, or subscribing, or perhaps even like supporting the channel. Either way, thanks for dropping by, and hopefully I'll see you around. Bye bye. As for the stream here, I probably should be grabbing something to eat, and yeah, I'll consider doing the shadow stuff. But in general, Mr. Yes, it depends on what you're trying to do, how you should rotate things, because let me just commit these things here and upload the video. Uh, uh, oh, thank you very much, and you too. Are you doing anything interesting? All right. I'm just gonna spend the night and the evening with the missus. Gonna order some food and yeah, just try to have a good time. Nothing fancy. But I hope you'll figure something interesting out. Maybe at least some nice food or something. You could do some ordering in my country during the midday, and then you can go pick it up, and then you can maybe assemble the dishes yourself, or do the last bit of cooking in terms of just heating it or arranging it, or yeah. I think takeaway might not be as viable, but usually a lot of restaurants do a bit of food preparation during the morning and midday, which they sell. At least in my country, but I don't know about yours. Mm. Yeah, you're absolutely right. Um, I also um, thought about doing that. I probably will do the shadow part, at least a simple shadow rendering pass, and then I will create a better thumbnail with images from from the series, so that anyone who clicks the the thumbnail will see what they actually can expect from the last episode. So yeah, but I think you're definitely right. I should do better thumbnails. Uh, but I think I need to go grab something to eat and do a nice long break. I might be doing one last episode. I might not. Maybe I'll do it tomorrow. Maybe I'll do something else. But yeah, I definitely feel hungry, so I should get that sorted. Let's see. Yeah, that is truth. Uh, but yeah, we will probably implement the shadows, then create some nice thumbnails. Maybe I'll even cheat a bit and well, I'll do this shadow episode and I'll then cheat a bit and use my OBJ model loader. No, 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 it's no problem. I'll try to get them sorted myself, but thank you. I just wanted something to actually resemble what the project would result in, so um, therefore I've been waiting a bit in terms of creating a thumbnail. Um, well, we'll see how nice the thumbnails turn out when I do them, but if you can do them better, I'll consider letting you do it instead. But uh, you shouldn't feel obliged to. I think I can turn out a nice thumbnail or two. Anyway, eh, yeah. But I think that maybe we should do the shadow episode before we do thumbnails. But um, feel free to send me something uh, if you have the time for it and so forth. They're definitely better than my current thumbnails anyway. And since we're waiting on the shadow episode, yeah, we might as well. If you could do a basic thumbnail that I can use for all of the videos, I can change thumbnails of all the videos individually. That's no problem. Um, but I'll do a thumbnail which uses the program that we create. So, um, for instance, I'll when we do the scene, uh, eh, it's fine, whatever. You don't have to do it. So just whatever you feel like. Just bear in mind, eventually I'll do a thumbnail as well, and I'll definitely fix it. I just wanted to maybe do the shadow casting here. Oh, don't worry about it, man. Don't stress about it. But sure, if you want to, I'll appreciate it. But yeah, I'll do the shadow episode, and then I can use the program to actually render something that looks decent and I'm afraid I'll lose that competition, but sure, we can do a competition. I'll just do the shadow episode first. Anyway, buddy, I gotta go. I'm starting to feel really hungry. If we do not talk to each other before New Year's Eve, I hope you have a great evening, and hopefully I'll be seeing you around the channel. Take care. All right. See you around, buddy. Happy New Year's. Bye bye.